In this video I will be discussing the relationship between the Pearson correlation and the slope of the linear regression line. So whenever we have two variables, and we're just going to be in a case where in the state where we have two variables, x and y. If we have more than two variables, then what I'm saying now has to be modified, but let's just take the simplest case where we have a dependent variable y and an independent variable x, the Pearson correlation between the two variables, and the slope of the linear regression line. There's a relationship between them. Remember from the previous lecture and from the lecture notes, from the previous video and from the lecture notes, that the Pearson correlation between x and y is given by the following formula. It's the covariance of x and y scaled by the product of their standard deviations. And if you go back to the previous video, you will see that we arrived at a different way to rewrite both the numerator and the denominator so that we could calculate it by hand. For the numerator, we rewrote it in this way. And in the denominator, it doesn't really matter the way we wrote it, but for the purpose of this lecture, it doesn't matter. We're not going to get into that right now. You know the way we rewrote it. You can go back to the previous video. I could write it, but it's not going to affect what we're going to do. We're just going to look at the numerator here. Now, it turns out that there is a relationship between r and b hat that most students they get confused about the different distinction between correlation and the slope of the regression line. Now, b hat, if you recall from the lecture notes, let's go back and do a brief overview. If we have a set of data points, so two variables, y and x, and we have data on each variable. Here we had 6 data points on each variable. And if we take the points and plot them in a scatter graph, then the question we asked in the lecture was, what's the best line that passes through these points? What line would best represent the linear relationship between y and x? Clearly there's not a perfect linear relationship. No line goes through every point. But is there a line that passes through these points in the best way? If that makes sense. And the way we defined best was we wanted to figure out if there was a line that we could draw such that when we drew that line and we calculated the error at every x value, we calculated the difference between what the line says the y should be and what the actual y should be, and we added up and we squared those differences, and we added up the sum of those squared errors. We wanted the line that would give us the smallest. Is there a line that exists that gives us the smallest sum of squared errors? Or maybe there are 2 lines that give the same smallest sum of squared errors, or 3. And what we found in the lecture note, in the lecture here, is when we minimize the sum of the squared errors, it turns out that there's only one line that does that. And it's a line where the slope of the line is given by this formula, and then the y-intercept is given by this. Remember that 2 parameters uniquely determine a line, or completely determine a line, right? The slope and the y-intercept. So we found this line right here where there's the slope and here is the intercept. This particular line is the only line that minimizes the sum of squared errors. There's only one line, so there's a unique solution to the problem that we were trying to solve. Now let's take this b hat. Here's the formula for it. All I'm going to show you is that b hat and r, the formula for b hat and the formula for r, are related to each other. You can get one from the other and vice versa. In showing you this, I think you will see how that r and b hat are not the same thing, but they are related. So b hat, just copying from the lecture notes, is the sum of xi minus x bar times y minus y bar in the numerator. And in the denominator we have the sum of the xi minus x bar squared. So let's write that here. I'm going to suppress the I equals 1 to n, because you know that's there, but it's just extra writing that I don't want to have to do. So that's the numerator, and then in the denominator we have this. Now, just looking right now, it's hard to see how b hat and r are the same. I'm sorry, they're not the same. It's hard to see the relationship between b hat and r just looking at it, just looking at this. It turns out, though, that the numerators of both r and b hat are the same. In other words, this, I'm sorry, that's not completely correct. It turns out, first, if you multiply both the numerator and the denominator of b hat by 1 over n, then the resulting b hat then in the numerator, the resulting b hat is the same as the numerator of r. Notice we haven't changed b hat. We just multiplied the numerator and the denominator by the same thing. So we get the same answer for b hat, right? Because the 1 over n cancels with the 1 over n. But now, written this way, this numerator right here is actually the same thing as this, and is the same thing as this, obviously, then, because these two are the same, right? So this is the covariance of x and y. It's just written in a different way. Now the denominator of b hat is actually, if you look carefully at it, you should be able to tell what that is. That's just the variance of x. You take each x value, subtract the mean, square all those differences, add them up, and take the average of those numbers. Divide by n. That's just the variance. So let's take the numerator of b hat and show you, use some algebra to show you that it's actually the same thing as the numerator of r. It's the covariance. Let's take this 1 over n times this sum. Now let's expand the sum. So we're going to have xi times yi minus xi times y bar minus x bar times yi plus x bar times y bar. And we're taking the sum. But since this is a sum inside of here, right, we have xi, yi plus a negative xi y bar plus a negative x bar yi plus x bar y bar. It's a sum. Since we have a sum inside here, then the sum of a sum is the sum of the individual sums. It's the same thing, right? In other words, a plus, if you take the sum a plus b plus c, that's the same thing as a plus b plus c, right? So that means that we can pass the summation sign inside across all these terms. So let's do that. So all of this is equivalent to 1 over n. Just bring 1 over n out. And then we have the sum of xi yi minus the sum of xi y bar minus the sum of x bar yi plus sum of x bar y bar. Close the bracket. So this is the same thing. And then we can simplify each of these terms. Well, not necessarily each of them. This one can't be simplified anymore, just the sum of the xi yi's. I'm suppressing the notation, right? I equals 1 to n, right? But keep that suppressed. I think you know, you're comfortable with this already. If you watched the last video, you should be. Now, the sum of xi y bar. What's that? That's y bar times, if we actually wrote the sum out, it would be y bar x1 plus y bar x2 plus y bar x3 plus all the way out to y bar xn. Y bar is common to all these terms. We can bring it out. So that's y bar times x1 plus x2 plus all the way up to plus xn, or y bar times the sum of xi, where I goes from 1 to n. So this y bar, since it's a constant, we can pull it outside the sum. And rewrite it like this: y bar times the sum of the xi's. Now, using the same logic, we can also do the same thing to sum x bar yi. Since x bar is a constant, it's just the mean of the x's. It's a constant. It's a number. It can be 2, 3, 4, whatever. We can pull it outside the sum. Now, what about this term? This is really x bar y bar, if we wrote it out, plus x bar y bar, plus x bar y bar, plus, and you do it n times. Right? What's common to each of these terms? X bar y bar is common. So x bar y bar times 1 plus 1 plus 1 plus 1 plus, all the way out to plus 1 n times. What's 1 plus 1 plus 1 n times? That's just 1 times n equals n. So x bar y bar times the sum of 1's, n of them, is just n times x bar y bar. So we've gotten it down this far. Now we can pass this 1 over n inside of the brackets. Now it's 1 over n times y bar times x, sum of the xi's, minus 1 over n times x bar times the sum of the y's, plus 1 over n times x bar times y bar. That equals 1 over n times the sum of xi, yi, minus. Now, what's 1 over n times the sum of the xi's? That's just x bar. That's where you add all the x's up and you divide by n, divide by the number of them. So really we have x bar times y bar. Same thing over here. What's 1 over n times the sum of the y's? That's y bar. And then this final term, what's 1 over n times n? Well, that's just 1 times x bar y bar. Excuse me. So now we have minus x bar y bar minus x bar y bar. That's minus 2x bar y bar plus x bar y bar. That just leaves a minus x bar y bar. And then we can take it one more step, or a couple more steps here. X bar is 1 over n times the sum of the x's, multiplied by y bar, which is 1 over n times the sum of the y's. Now, 1 over n times 1 over n is 1 over n squared. So we can write it like this. And then what's common to this term and this term? 1 over n. We can bring the 1 over n out, and we have sum xi, yi minus sum x bar times, sum xi times sum yi. So this is the numerator of beta hat, because we took it down here and we rewrote it and rewrote it and rewrote it until we got it to a form that looks like this. So this is the numerator of b hat. Look carefully at that. That's exactly the same thing as the numerator of r. They're the exact same thing. Oops. Put this right here, right? I forgot to, it's 1 over n times this minus 1 over n squared. I just forgot the 1 over n, but they're the exact same thing. So this is the covariance of x and y. So the numerator of b hat is the covariance of x and y. So now let's go and write a formula that will express b hat as a function of r. So b hat really is just the covariance of x and y over, and what was in the denominator of b hat? We said the denominator right here is the variance of x. So the slope of the regression line is the covariance of x and y divided by the variance of the independent variable. So the variance of x would be the standard deviation of x squared. So that's b hat, rewritten. And then the Pearson correlation between x and y is the covariance of x and y divided by the product of the standard deviations of x and y. Clearly you can see that there must be a relationship between these two. You can get one from the other excuse me. You can get one from the other and vice versa. So what is the particular, or what is this relationship between b hat and r? Well, it turns out it's this. If we know r, then we have to know the standard deviation of x and the standard deviation of y. Because to get r, we have to calculate standard deviation of x, standard deviation of y. So if we know r, then we can know b hat by just using this formula right here. And you can verify that this is true. R is covariance xy divided by standard deviation of x times standard deviation of y. If we take that and we multiply r by standard deviation of y over standard deviation of x, what do we get? Standard deviations of y's cancel, and we get covariance xy divided by standard deviation of x times standard deviation of x. That's the standard deviation of x squared. That's the variance of x. What is the covariance of xy over the variance of x? It's b hat. So we verified the formula above. So definitely put this formula in your notes. And here you can see, with the formula, you can see that r and b aren't the same thing. Whenever the biggest r can be is 1, right? rxy equals 1 whenever the covariance of xy equals the product of the standard deviations, right? Because r is the covariance over the product, and the covariance over the product will be 1 whenever the covariance, the numerator, equals the denominator. And so whenever r is 1, we can just put r equals 1 in right here. We can see that beta hat is equal to the standard deviation of y over the standard deviation of x. That makes sense, right? If covariance xy equals standard deviation of x times standard deviation of y, then beta hat equals covariance of xy over variance of x equals covariance of xy whenever r is 1 is this, and this is just equal to standard deviation of y over standard deviation of x. That's what b hat is whenever r is 1, just like this formula would suggest. And so again, to reiterate, if we have x and we have y, and suppose all points pass through the same line, then we know that r xy is will tell you the extent to which the points pass through the same line. If they pass through the same line, and that happens with the highest extent. So r is as big as it can be 1, and then b hat just gives the slope of the linear regression line. Now, if the points all lie in the same line, the linear regression line is that line that passes through every point. But if the points don't lie in the same line, so suppose we have something like this, maybe this one's way out here, then maybe the linear regression line would look something, I don't know, something like this. You have to calculate it. b hat would be the slope of this line, whatever the slope is. And r is the extent to which every point lie on this line. And that didn't happen very good with this data, right? So r for this data set, the rxy, might be equal to, I don't know, you'd have to calculate it. But in general, it looks like there's an upwardly sloping trend, kind of, right? It's kind of upwardly sloping. So r might be, it looks like a linear trend, possibly. Maybe r is like 0.3, for example. Something less than 1 for sure. R just is the extent to which the points all lie on the same line. And beta hat's the slope of the line. The slope could be 2 or 3 or 4. It's not 0.3 necessarily. All right. And then one final thing, if we have r, we can get beta or b hat. But you can always express r as a function of b hat, right? So if we have b hat, we can get r. So we could rewrite this as rxy equals b hat times standard deviation of x over standard deviation of y. So this would be the inverse function of this one. So this concludes the video on the relationship between the slope of the linear regression line and the Pearson correlation coefficient.